Question 14, a classic kind of question. Try not to get bogged down with the using of the Fleming's left-hand rule here. This is a question looking to compare magnetic forces experienced by moving charged particles and electric forces experienced by moving charged particles. And this is linked very much to the lesson that we did on the velocity selector, so if you feel the need to review that lesson, you should. Okay, so we've got a positively charged particle travelling in a uniform field. It doesn't specify. Figure 21.1 shows the particle travelling at right angles to the direction of the field. Still not quite sure what the direction of the field is, so it's being very vague. Down in the picture we've got the direction of travel indicated by the arrow, that's fine, and the field is perpendicular to the plane of the paper, so that means the field could be either going into the paper or coming out of the paper. It could be an electric field or it could be a magnetic field. Describe the motion of the particle. So the motion, we know that E fields produce projectile motion, and we know that B fields produce circular motion due to the nature of the forces that they produce of a particle in terms of the force it experiences when in the field. If the field is a magnetic field, okay, so we've got 2 marks here. So I think one of the marks may be available for saying that it will produce circular motion, and the other one is going to be for the reason why it produces circular motion, and that reason is going to be linked to its force. So in a magnetic field, the force, I don't think this is going to be point scoring, but it was F equals B QV, and we know that the force due to the magnetic field will be always perpendicular to the velocity. So if this is our particle and it has a velocity in this direction, the force due to the B field will always be at right angles to it. This will cause circular motion. Okay. Now, with an electric field, the direction of the force will always be in the same direction as the electric field is acting. So because the electric field is uniform, the direction of the force is going to be in the same direction. And when you have a situation like that, you'll end up with projectile motion, much like you get with cannonballs being fired. So let's start by trying to recreate what we've written here, but in the context of an electric field. So let's start with the force due to the electric field will have a constant direction and so will produce projectile motion. Okay. Part B. Again, we have a uniformly charged sphere. So a couple of things that I'll be writing down would be the capacitance of that charged sphere would be 4 pi epsilon naught capital R, where capital R is the radius of the actual sphere itself. The question starts gibbering on about electric potential at point X, blah de blah. So I'm going to write down the electric potential equation just in case. Q over 4 pi epsilon naught R naught squared. And this r, little r, is always the distance from the centre of the charged object, always from the centre of the charged object. Very important when looking at this question. Okay, the electric potential at point X, so over here, at point X, V at X is plus 1,800 volts. Okay, that's fine. And the distance from this charged object would be, so little r x would be 2r plus another one, that would be 3r is the distance there. From the surface of the sphere, you can see that they're trying to highlight the potential for errors here. So it's not, 2r is not the distance to be used in this equation here. 3 capital R is the distance to be used. So these answers are nice and easy to do if you know all the tricks in order to get the answers nice and easily. And for me, the trick is going to be, instead of using the full equation, V equals Q over 4 pi epsilon naught R, calculate the electric potential at the surface of the sphere. It's much easier for me to just do a proportionality equation. So the only thing that's changing, the charge on the sphere isn't changing, these constants aren't changing, so the potential is proportional to 1 over the distance. And the distance is going from 3r the distance is going from 3r all the way down to 1r, so it's reducing by a third. So if I were to put that in here, 1 divided by a third, that would be 3. So what I'm expecting is the potential as I move from X to the surface of the sphere to increase by a factor of 3. So that would be 3 times 1,800, producing a potential of plus 5,400. I can't remember where we got to, so I presume times the 1,800 given to you on the previous page by 3 to get 5,400 volts on the surface of the sphere. Next part of the question, the radius of the sphere is 4 centimeters. Calculate the charge on the surface of the sphere. So we're going to need this answer to solve this part of the question. Let's start with the equation V equals Q over 4 pi epsilon naught R. Well, I can either use the voltage of 1,800 and a distance of 3 capital R, so 3 times 4, or I can use this voltage and a distance of 1 lot of that. So I'm just going to use this one. The charge would be potential times by 4 times by pi times by epsilon naught times by R, so it's going to be 5,400 times by 4 times by pi times by 8.85 times 10 to the minus 12 times 4 centimeters, that's going to be 0.04, not squared, and on the calculator, and we get 2.4 times 10 to the minus 8 coulombs there. That's the charge stored on the sphere. Part 2, calculate the electric field strength at the surface of the sphere. There's 2 ways we could do this. Either go in guns blazing with the big equation, E equals Q over 4 pi epsilon naught R squared this time, and we know the charge on the sphere, 2.4 times 10 to the minus 8 divided by 4 times pi times 8.85 times 10 to the minus 12 times by surface of the sphere, so the radius of the sphere 0.04 squared, and we can get there 2.4. We can either get 1, 3, rounding up 5,000 newtons per coulomb to minus 1, or we can take advantage of the fact that we understand that electric field strength between 2 charged plates gave us in a previous lesson the potential difference divided by the distance between those plates, or the potential difference divided by the radial distance between charges, so we could literally just go the electric potential from over here, 5,400. If I was to divide that by another radius, 0.04, I should end up with the same answer, 5400 divided by 0.04, and I get exactly the same answer, 135,000 newtons per coulomb. So definitely my answer here is going to be 135,000 newtons per coulomb.